Let's now turn away from these ideas. Let's assume that if we have a sample unit called a quadrat down on the shore, we are able to count what's inside it. So let's assume which we're able to do that. And now we need to think about how many of these sample units we actually take. Now obviously if we take hundreds and hundreds and hundreds, we can actually measure the whole population. And that would be great because we would be very reliable results and it would be extremely representative of the true population. But of course, as we've just said, it's almost impossible in some areas because they're too big, but also it's a trade-off with time as well. Now I know most of you would love to spend weeks and weeks counting snails on the shore in the rain and the sunshine. But the point is it actually worth your time to do that? Can you actually get a good representative assessment of the population without spending weeks and weeks of time? This is the idea of trying to understand just how good our assessment is. Well, I'm going to show you very simply, most of you have been through this before, it just helps illustrate the point of how increasing the number of samples, or what we call replicates, can actually increase how representative your assessment is. If we take one count of sea urchins, this is abundance and that's frequency on the y-axis. Say we end up with 4 sea urchins here. Is that likely to represent the population? Yes or no? No. It's not likely, but it could. It could be that 4 sea urchins per meter square was the mean value. It could be, but it's unlikely. So we're obviously going to do a few more counts. If we do 3 different counts, we can now calculate a mean. Hooray! We've done it. We've got a mean. That's all I needed. Remember I said we needed the mean? And we need standard deviation. We can calculate standard deviation. We can go home now. Okay, you get a mean value. And you can calculate a mean. You could put on 5 or 6 decimal places. It could be 6.783 sea urchins per meter square. And in an assessment report, that looks fantastic. Oh, I said, wow, that's really accurate. No, it's not. Okay, when you look at the sample size, it's only 3. So you have to be a little bit careful when you look at numbers in reports. Always check to see how much sample effort has been put in before you actually go, wow, that's really impressive. Decimal places are not impressive. If we add a few more, we can obviously change it. And what you see is the mean shifts slightly. Okay, it was over there when we started, then it came back here, now it's gone there. And we keep on doing this game. Thank God we're not going to do it for real. And you actually see the mean shifts a little bit now. It was moving a lot, moving a little bit more. Until in the end, if we keep on collecting and collecting and collecting, we'll get the true population and we can calculate the true mean and we can calculate the true standard deviation. The question here is how many replicate counts do we need to take? And how can we work that out? And so we're going to turn now to a little simulation that shows you the effect of increasing sample size on the representative nature of the mean, the standard deviation, and the standard error. Now, are you all still awake? Fantastic. The Walking Dead. That's me. You're sitting down. It's fine. So this basically is looking at sample size. So this is 3 quadrats, 5, 10, 20, 30, the rest. This is looking at the mean, the assessment of the mean. This is the standard deviation, and this is standard error. And each of these dots represents a little computer simulation. So there's a population on the computer, and they took 3 quadrats and got that value for the mean. And they did it again and got that value, and again and again. So there's 20 estimates of the mean here of this population with 3 quadrats. Make sense? Yep. And then there's 20 of 5, 20 of 10, blah, 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 blah. Okay? And what you can see from this, and I've just joined the dots because I hoped it would make a nice face or something, but what you can see from this is that the estimates where we've got very low sample size, the estimates are wildly non-representative. We can go from almost 150 down to maybe about 70, depending on which 3 quadrats we happen to choose. So these are clearly not reliable, and they're clearly not representative. It could end up that we did get one which ended up being representative, but most of them are not going to be representative of that population. Does that make sense? If you say yes, we'll finish quicker. Okay? Yes, you're up for that. Yeah, I want to go home. Yeah. Get rid of this guy. He's just flown from Hong Kong. Who cares? Yeah, okay. Oh, she looked after my drink. We're okay. We're pals. If we look at the variance, or we can turn it into standard deviation, what we can see is that, again, it's wildly all over the place here. But as we go on, it actually starts to stabilize. So both of these here are actually stabilizing. The more samples we take, the more similar they become, because they're now more representative of the true population. What's noticeable is that if we compare between 20 and 50, there's actually not that much difference. If you look at how much your estimate has improved between 20 and 50, you've probably improved your estimate, made it more like the true mean by maybe only 5 or 10%, but you've put in more than double the amount of work. And so the question here is, how much work do you need to put in? Do I really need to do 50, or can I actually get away with 30? And that depends on just how accurate you want your estimate to be. If you want it to be as close as possible to the true mean, then obviously you have to do lots and lots of samples. If you're willing to accommodate maybe a 10% error, then obviously you don't have to do quite so much sampling. And so there's a trade-off here between precision and between being representative. If we look at variance, variance also gets closer, but it's again levels off. And that's because you're measuring the true variance. So that's the true spread about the mean. The really cool one is standard error. And standard error is basically a measure of, you all know what standard error is, right? Because you told me you did. Yeah, okay. So you all know why it gets close to being 0 the more samples we take. Yep? Excellent. Brian will buy you a beer afterwards. That's cool. Basically, the more samples we take, the more our estimate gets close to the true mean. And that means that the standard error will reduce to be close to 0. Okay? So this means we're getting a very good estimate of the true mean. But again, the question is, how much effort do we want to put in here to actually get close to that true value? Is everyone happy with that? It's the only thing I'm going to show you tonight which has any sort of stats or anything to really get your heads around. Is it cool? If you understand this, this is from, I'm going to quote a lot from Tony Underwood today because he was really tight on all this sort of stuff. This is from his book, and he reckons if you understand this diagram, you can skip 4 chapters of his book. Okay? Okay, it's a 5-chapter book, so it's really not worth buying if you can do this, all right? So just think about it from that point of view. And these are the sort of patterns you get. Okay, so this is a real-life example, which we did 60 quadrats. Didn't sleep well for a month. And basically it shows you this is a population of snails. This is standard deviation here. And this shows you that still, even after we've done 60 quadrats, the standard deviation is quite large. And what that means is that this animal is really patchily distributed. In some places there's loads of them, in other places there's very few. And this animal likes to live in cracks and crevices. So it's restricted to those sort of areas and it isn't on the open rock surface, so it makes sense. And these down here show you how you can actually use these values to calculate how many quadrats you want to take. This one, for example, is looking at precision. So this is 10% here, so this is 90% precision. And this is looking at the number of quadrats you need to do to take that. So you can calculate from your data how good your estimate is. And what you need to think about when you go out to do these survey work is how much error you're prepared to accept. And this is where it comes down to thinking about how good your estimate really is. There are also some equations which you can use to work this out. I'll just let you, do you want to copy that down a minute? Okay. The point about this is if you work out this, and this again has the error which are allowable, you end up with some really scary numbers like 174 quadrats. How many did you do today? Or when is it the other day? The whole class? This saying you need 174 quadrats, okay? So we don't use this method, okay? This one's too scary. But the point is, it's really important, when you make an estimate of the population, it's important to know how good your estimate is. You need to know how much error you've got, because then you understand how repeatable and reliable your data are. So it's very important to look at that, because that will then tell you how much error you can tolerate. And if you're doing large-scale surveys, perhaps you don't need to be precise. You can tolerate perhaps a 15% error. If you're doing very precise surveys of one population on shore, which you're going to go back and look at again and again and again, then perhaps you need to tolerate only a 5% error. So it's important to make those decisions. Okay, let's just talk about, well, before I do that, do you have any questions? I can see John Lucas put his hood up. That means he's going to start to go to sleep. So if you just prod him occasionally, that would be really good. Is everyone happy with that? You don't have to be happy, but everyone's okay, yeah? Okay. Let's go on to how the samples are taken. Well, we talked a little bit earlier about statistics and about you must plan how you're going to do this assessment work before you start it. And one of the things most samples require to do is random. Okay, do you know what random is? What's random? Sorry? Do you hear what he said? In Intertidal ecology, the old way of being random was to take this wonderful quadrat unit and you used to throw it over your shoulder. Okay? But it was really random, honestly it was, because if you were right-handed, you put it in your left hand and threw it over your shoulder. Okay? You ready? If you were left-handed, you put it, that's great, yeah? Okay? So first of all, they need to be random. How do you get random? How can you get random? Not you personally. Random number generator. It's easy these days, right? But in the old days, it didn't used to be that easy. And so then in the old days, what you used to do is you used to go to the prettiest girl you could find, or hunkiest chap, and say, excuse me, have you got your telephone number? I need some random numbers for my quadrats. Okay? Works. Works. Never works, okay? So we need to have random positions of quadrats, okay? That means that we are not biasing where we put those quadrats, okay? They are actually placed in an area, because if we're biasing it, then it's not going to be repeatable, it's not going to be reliable. The other thing is they need to be independent of each other. We can't sample the same area, so we need to make sure that they're independent. And if we do that, we're ensuring we can use data for statistical analysis, which is what we're trying to aim towards. So let's have a little look at how we might be able to do this, okay? We can't go out on the seashore because it's dark, health and safety won't let us, and anyway it's wet and cold and miserable here. So we're actually going to have a little situation where we're going to look at the distribution of urchins at a certain tidal height, okay, as a simulation. And I mentioned right at the beginning that tidal gradient was that very important vertical gradient. And so that's the gradient we need to measure when we're looking at the distribution of species. And what we're doing, if you like, is we're stratifying the seashore. We're stratifying it into different vertical heights. You need to be very careful about this. This is a beautiful PowerPoint which I drew about 10 minutes ago. That's not true. I drew it while I was giving this talk. It's amazing. And basically, a lot of people will run a transect line, school groups especially, from the top of the shore to the bottom of the shore. Just take a line straight down, and they'll do counts along that line. And basically, if you look at the seashore, it's not flat, okay? It sort of bounces up and down. And if you look at the height here, because this is the tidal height here, the tide comes in, the tide goes out. This point here is the same as this point. So actually throwing something, looking down the shore is not the real way to do it. What we need to do is to measure the real tidal height. And I know that's what you did, I think, with your transect lines there. You put a tidal height out. Fantastic. And you need to think about contour maps when you're doing that, okay? That's the best way to get a head around it. It's actually trying to think about a contour map where you actually follow contours in a terrestrial environment. So we don't put lines down here, which are nice and straight. We're always obsessed with putting things in straight lines, yeah? We always like to have nice straight lines. Don't let them batter you, okay? Don't let them influence you. What we need are actually contours that follow the contour of the rock. And then what we can do is we can put our quadrats randomly along these different tidal heights so we can make counts of our sea urchins. In this case, I've gone back to being old and boring because I can't draw all the rough things. But this gives you the idea. We can look at the abundance of sea urchins at 1.5 meters. We have a quadrat. We do a count of sea urchins. Is that going to represent the population? Yes or no? Come on, guys, we can finish this. No. It could. It could, right? It could represent. It could be 2 sea urchins per meter squared, but it's unlikely. The other thing is, of course, we have no measure of variation when we do that. If I'm very lazy, I don't like moving very far, I don't like random number tables, I can just do counts around me. Okay, that's nice and easy. And it's slippery and I don't like walking on seaweed. Okay? So, does this represent the abundance of sea urchins at 1.5 meters above sea level? Yes or no? Why not? It's not random, yeah, but it could represent them. But also if you look, they're all in one area, right? Because I'm lazy. We're actually only measuring that little tiny bit of shore. So if we're trying to measure along this tidal height, we're not measuring all the way along this tidal height. And so this is something where we actually look at these replicates. They don't represent that entire tidal height. They only represent one area. So they're actually not real replicates to represent that whole tidal level. And of course, what we really want to do is, by the miracles of PowerPoint, we want to have randomly positioned quadrats at these different heights. And then we can go and count the sea urchins, and we'll be fine. Make sense? Say yes. Yes. Fantastic. Okay. What about if we want to compare the sea urchins at two different tidal heights? This is 1.5 meters and this is 1 meter. Again, we need to make sure that these are no good. They don't represent those tidal heights. They simply represent this patch. And so again, we need to go and randomly assign the quadrats so that they are going to be able to measure all along that tidal height. So something like that would allow us to do that. They're randomly positioned, they're independent of each other, and they are dispersed across that tidal level. And so these are what we would call true replicates. They satisfy all the things we would need to be able to go and use statistical analysis. So now I hope what we've been able to do is be able to talk about some of the mistakes we can make and how we can fix those mistakes. So would we all be happy to go out, put a transect line at set height and do random quadrats, and we could do it all the same? Yes? Score? Yes? Okay. What about this one then? This is where I put the quadrat, right? But I didn't tell you where I was going to put them. We're on two different parts of the coast. You're over there, I'm in Hong Kong. I don't like putting my quadrat there. What I like is putting it there. Same quadrat, same random number. However, there's a difference here in tidal height completely. You come back and say, I found all these snails. I come back and find I found all these sea urchins. And the reason is we just put our quadrats in the wrong place. One of them is above the line, one of them is below the line. So even when we think we've got all these things covered, there are still ways we can screw up. So we've actually got to think very, very carefully about how we do this to make sure we get representative, reliable, and repeatable measures.